All right, take two. We're looking at the change in energy. How much work does it take in order to move a charge onto it? So we have this potential difference across the plates, but Q is what we're moving. So we're really concerned with dQ going onto the plate, so infinitesimally small charge. I know for a capacitor, that's equal to Q over delta V. So so delta V is equal to Q over C. So if I put that in here, I know that this infinitesimal change in the energy is equal to Q over C dQ. And I probably should use the same Q's there. So Q. Which is why it gets kind of funky when dealing with this about big Q, little q, so not 100% rule. If I integrate both sides, I'm going from 0 to whatever that final potential energy is equal to, well, the capacitance is based on the geometry, so that pops out, and I'm integrating Q dQ from 0 to big Q. On the left-hand side, I have U. And on the right-hand side, I have 1 over C times 1/2 Q squared. So the total amount of potential energy that gets stored on the plate is 1/2 Q squared over the capacitance. Now we can manipulate that and look at it in slightly different form. I know that the capacitance is Q over delta V. So if I plug that in, I get 1/2 Q squared divided by Q over delta V, which is 1/2 Q delta V. So it equals 1/2 Q delta V. And I know that the charge, based on this formula right here, Q is equal to C delta V. So I can plug that in and also get 1/2 C delta V squared. Now your textbook just says V squared. It's doing the shorthand notation of, since I can make the potential 0 anywhere, let's just make the potential 0 at wherever, someplace convenient, so that the final final potential is equal to the change in potential. All right, so we have 3 different expressions for the potential energy of a capacitor. Let's work through a problem using this. I have a parallel plate capacitor where the bottom just barely touches a fluid. I hook this up to a battery. Now this fluid has a density of rho. It is a dielectric. So if we look at an actual parallel plate capacitor, that if that's my positive and negative side, my electric field is going like this, and it is pretty well even across, but as you get near the edges, it starts to curve. So the liquid is going to be influenced by this electric field. Not enough that we're going to take that too much into account, just enough to justify the fact that this dielectric will be affected by the electric field if this is my positive and negative side of my plate. In the liquid, it's going to polarize the molecules. So I got negative, positive, negative, positive, negative, positive, negative, positive. And it will start to attract to the sides. In other words, this liquid will start to rise between the plates. Now, in this particular problem, let's assume that it rises up to the top of the plates. So the question is, what is the dielectric constant of the liquid? Give a couple of things here. The distance between them is d. The plates are square, and they're h by h. All right, so I know that before we put this, before any liquid really gets sucked up, the amount of energy stored on this is 1/2 the capacitance delta V squared. As the liquid gets sucked up into it, well, the plates are going to change. The amount of energy stored on the plates will change. And so the energy stored on the plate, 1/2, well, instead of C, we throw a dielectric constant into it. It becomes K naught C delta V. Or just put it 0 there, 0 there. And so the change in the potential energy stored on the plates, so the change in potential energy stored on the plates is going to be 1/2 kappa C sub naught delta V sub naught minus 1/2 kappa naught delta V sub naught squared. So that's 1/2 times kappa minus 1 C sub naught delta V sub naught squared. Makes so much sense when I write it down. All right. I also know that the change. Okay. So I had a certain amount of charge on the plates. When the dielectric goes into it, I'll get more charge on the plates. My voltage is staying constant there. So I've got more charge on the plates. So I'm not worried about the energy it takes to get the charge on the plates. That's taken care of right here. I'm talking about the energy that's actually on the plates because I have a charge there. I know that delta U is going to be equal to whatever the new charge is. Delta Q delta V. Which one of those days, is it? All right, one moment. No, that's why it didn't make sense here, because that's wrong. change is equal to the change in charge times delta V. Dielectric comes up, we get more charge on the plates. The potential energy, the amount of work that goes into changing that charge is this. And that's going to be equal to the change in energy, which would be Q final delta V minus Q initial delta V. The math notation is horrible here, but I'm going to go with it. This is kappa times the initial charge, delta V minus Q initial delta V. So this is kappa minus 1 Q naught delta V. And seems like I'm going the wrong way around, which is kappa minus 1 C sub naught delta V squared. So this is the potential energy. The change in potential energy because of the dielectric coming into it. This is the change in potential energy of all the excess charge. That's stored now. And so the amount of energy it takes to pull the liquid up has got to be the difference between the two. So the change in potential energy to actually suck that liquid up is going to be equal to the difference between those, which is just 1/2 kappa minus 1 C naught V naught squared. And we're pulling that liquid up. What kind of change in potential energy are we talking about? As the liquid gets pulled up into
increase.
Sorry?
Increase in potential energy.
What type of potential energy?
Gravitational.
Since the liquid's filling up this entire area right here, this obviously not a lot of change in potential energy, gravitational potential energy. This has the most, but we can pick the middle spot. So it's going to be 1/2 mgh. We're dealing with a liquid here, so it's 1/2 times the density times the volume, gh. The volume is 1/2 rho times, well, the volume of that rectangular solid there, it is h squared d gh.
Where did that 1/2 come from?
This 1/2?
Right before that.
That one?
Yes.
Looking at the difference between the potential energy from the charges and the potential energy from putting the charges on the plate.
1 minus 1/2. Okay,
Yeah.
I see.
So at 1/2 kappa minus 1 C naught delta V squared equals 1/2 rho G D H cubed. Distributing 1/2 kappa, since I'm solving for kappa, 1/2 kappa C naught delta V squared minus 1/2 C naught delta V squared equals, well, the 1/2s can go away, so let's do that. Equals rho G D H cubed. add that to the other side and divide, or divide and subtract, add, however you wanna do it, but kappa ends up being rho g d h cubed over c naught delta v squared plus 1. We can take it another step, because we're dealing with a parallel plate capacitor, and I know the parallel plate capacitor, at least C sub 0 is epsilon sub naught, A over D. I know A is H squared, so this is epsilon naught H squared over D. Plugging that in for here, we end up with kappa equal to rho G D H cubed over epsilon naught H squared times D over delta V squared plus 1. And most of the H's cancel out, the D's combine, and I get rho G D squared over epsilon naught, H, epsilon naught delta V squared plus 1. Anyway, obviously, I hope it's obvious. I have not presented this before, and I thought I'd go for it. Win some, lose some. I want to do one other thing, at least one other thing with capacitors. Any questions?
What is rho in this equation?
The density of the liquid.
Okay.
We are ignoring any capillary action. No meniscus. No loss because of viscosity or drag. All right. This next one actually comes from a 152 student who did part of the lab wrong. You had the parallel plate, you had dielectric in between. Now in that second part, when you were supposed to move the plate, so, you know, in theory, you have the plate like that, you have the dielectric, and then the other plate shifts down. And you're looking at the overlapping area. Presumably, that's what you did. Looking for some recognition. Okay, I have at least 3 knots there from 2 different groups, so we're good. Now, what the student did instead, or what that group did instead, is they shifted the paper down. So we have a slightly different situation. So if I have a gap of D, let's make the distance the paper shifts is X. And the question is, how should the capacitance change based on this? Because I have part without a dielectric and part with a dielectric. Well, if we think about it, I have this dielectric with nothing in between, I have a capacitor with nothing in between and a capacitor with dielectric in between. They have the same potential difference between both sides, but what's different, or this is the equivalent of 2 parallel capacitors, one of which has no dielectric, the other one has a dielectric. So if this dimension here is, we'll make it H by W, so the area of plate is HW. I did the length and width. Which one? Do you remember which one I made length and which one I made width? Length was this way, width was this way. 2 days ago.
length was parallel with the edge of the table.
Okay, so this was length, and I called that width. All right. So I'm gonna treat this as I have a capacitor here, a capacitor here. This is a dielectric. The length of the side is, the width is W minus X. And this has a, that one would just be, so I'm moving it that way, so W, yeah, X. And they both have a length going in and out the board. And I want to find the equivalent capacitance. They're in parallel, so I know that my equivalent capacitance is just C1 plus C2. What's the capacitance here? Parallel plate capacitor formula.
Kappa epsilon sub naught,
Kappa, epsilon,
sub naught, and then area over distance.
all right, so that's 1, 1, and 1, plus kappa 2, epsilon sub naught, A 2 over D2. D is the same for both, in theory. Kappa 1 is 1. It's air, it's 1.000 something, close enough to 1. So I have epsilon sub naught, A1 over D. Oh, I know what I can find A1, not equals. Plus kappa 2, or I'm just gonna write kappa, that's what we're trying to find in that lab.